Hello. In this video I'm going to reproduce the talk that I gave at the Pint of Science Festival on Tuesday the 16th of May this year. The title of the talk is What Turing Missed, Purpose in the Machine. Now, this is a bit outside my comfort zone doing this talk, being a psychologist and talking about artificial intelligence and computers and robots, but actually one of the reasons why I got fascinated in Alan Turing's work is that when I was working in Manchester for many years, it turns out that I was actually using Alan Turing's old office in the Coupland 1 building, where he was doing his work on morphogenesis, which I'll tell you about in a minute. And I'd been interested before that, but since that time I read a lot more, and that's led to the angle that I've got for you today. Okay, so everyone knows about Alan Turing's amazing contributions, both in terms of the development of the modern computer and in terms of his contribution to code breaking for drawing World War II to a close, arguably early, saving millions of lives. And those two incredible feats have made him now such a well-known and well-recognised figure. His work on morphogenesis is less known. This was his last paper in 1952, and he decided to work on trying to understand the mathematical basis of how the shape and structure of life forms develop, such as the patterning of stripes and dots on an animal's skin, for example. Now, people have often asked, why did he make this shift? And also, why was he always so fascinated in creating first artificial intelligence and then using that mathematical knowledge to understand what's really at the heart of life? And several autobiographies have pointed to the profound story of when Alan Turing grew up. He had a very close relationship with another boy called Christopher Morcom, and tragically that boy died when Turing was 17, and it's been argued that that traumatized Alan Turing very understandably, and that it also set pace his drive to try and recreate and reproduce life. Now, related to this other point, to this whole point, is an essay that Alan Turing wrote called The Nature of Spirit, and he wrote this 3 years after Chris Morcom had died to Chris Morcom's mother to console her. But in that essay he reveals his beliefs about the spirits and spirituality, and I was struck when I found this out, that a scientist of such mathematical rigour also held on to what is essentially a supernatural belief about spirits. And just to give you a really clear idea of what kinds of things he was saying, here's a quote from that essay. As regards the actual connection between spirit and body, I consider that the body, by reason of being a living body, can attract and hold on to a spirit, whilst the body is alive and awake, and the two are firmly connected. When the body is asleep, I cannot guess what happens, but when the body dies, the mechanism of the body, holding the spirit, is gone, and the spirit finds a new body sooner or later, or perhaps immediately. And in one of the autobiographies called The Man Who Knew Too Much, it's clear that Alan Turing held on to his spiritual beliefs right through to the end of his life. And so he seemed to hold on to this understanding of human nature, where he saw the personality and the intentions of people as spiritual, at the same time as developing an extremely mechanistic model for how intelligence works. And I've drawn attention to Alan Turing to really draw this out as a distinction, but I think Alan Turing was really just echoing a division, a dualism between the spirit and the body that actually, I would argue, has continued right through to the present day and actually affects psychology, it affects our culture, and it affects, in practical terms, how we design robots and limits them. So I want to say a little bit more about why I think there's this split and why Alan Turing wasn't actually unique. Here's a nice cartoon of Alan Turing's invention, the universal machine. This is at the heart of all modern computers, and Alan Turing wasn't the only contributor to this, but he's certainly credited with some of the pivotal insights. The beauty of a Turing machine is that it's universal, and so it can, as you know, with a computer, lend itself to all kinds of processing, and it does it in a very simple linear way. It takes in input, it processes it, and it generates an output. And at the fundamental hardware of the computer, that is just in ones and zeros that are coded on microchips. So it takes a very linear cause and effect approach. It takes in input, processes it, sends on output. And that's the beauty of computers, and that's why they do what we want them to. And obviously computers are also, as we know, digital in this present age. That's what the ones and zeros represent. They represent distinct values rather than a continuous measure of something. But this wasn't always the case. There are digital elements in our environment and there are analog elements. And here's the classic difference. You see a digital clock, which presents things in discrete numbers, and you see an analog clock where the hands sweep round in a continuous way. And back in the 40s, when Alan Turing was really crystallising his work on computing, there were two kinds of computers. There were analog computers as well as digital computers. And in analog computers, elements of the hardware and their properties, so these might be valves and various physical components in older computers, they actually mimic the continuous properties of things in our environment, such as the length of things, the heat of things, the distance from things. If you think about it, our environment in many ways is a continuous, we can measure things in a continuous manner. And here's an example of an old analog computer that was used to simulate the flight of a jet aircraft back in the 50s. So clearly in those days there was a genuine race between analog and digital computers, and we know exactly who won that race, the digital computers. But I'm going to put it back to you that may have had its day, and it may be time to return to the analog. But there are good reasons why the digital revolution took off and why we don't have many analog computers these days. The digital computers, credited in part to Turing, could achieve all kinds of feats. And actually Alan Turing wrote the first ever code for a chess program on a computer. And we know how powerful computers are in competing at chess, and that was established very early on and really set the stage for digital computers taking the forefront. Now, why have I got a picture of God up here pointing at human beings? This decision to go into digital cause and effect, input-output ways of understanding computers, I would say was in part, has its origins right back in the Enlightenment period, where science started to fully break away from religion, where people would not need to invoke supernatural elements in their scientific discussions. And as we know, with religion comes a sense of purpose, a sense of destiny, a sense of divine fate, And what appears to have happened in the development of science is, in the attempt for scientists to be rigorous, they distance themselves from the purposefulness, the teleology of religion. And that's clearly the right thing to do when you're modelling physical objects that don't have their own intentions and purposes. But I'm going to put it to you that scientists, even in the behavioural scientist area, and psychologists did the same thing, and thought, and are still proposing, that the right way of studying and recreating intelligent beings is in this cause and effect way, because the idea of a purpose has been put to one side. And this was a point that Bill Powers, who I'll talk about in a minute, made, and really sees at the heart of why theories within psychology have not fully rigorously tried to emulate purposeful processes. The other reason, I think, why people, when they try and develop psychological theories or build robots, tend to focus on this input-output way of doing things, is that they're genuinely afraid of giving robots their own purposes, their own intentions, their own desires and their own needs, because there's a fear, as exemplified in the Terminator movies, that if you give robots their own intentions, they'll take over the world and dominate us. And so I think there's a number of quite good reasons. The success of digital computers, the distancing from purpose as part of science, and the fear of modelling purpose in an artificial agent, that I think has taken our whole direction in terms of understanding human nature and producing robotics in a direction that I would say is not going to be fully successful. Now, this is ironic in itself, this departure, because there are machines that are purposeful, that have very simple purposes, and model them in a very ingenious manner. This is what's called the Watts governor. This device is what's responsible for keeping the speed of a steam engine constant, regardless of how strong the coal is burning and the steam is flooding into the engine to power it. And it does this through these balls that rotate at the top of the shaft. As the steam comes into the steam engine, it rotates the shaft faster. As it gets faster, because of the centripetal force, the balls raise upwards. That upward motion actually acts against the input of the steam coming in. It closes a little valve so that less steam comes in the faster the shaft moves. So what this means is, by adjusting the weight of the balls on the Watts governor, you can keep the steam engine at the exact speed you want it to be. And this is called negative feedback. And the interesting thing about negative feedback is that it's present in all kinds of technology that we already have, in keeping the angles of flaps of aeroplanes at a constant angle despite the forces on them, guided missiles, thermostats, factory production lines. All of these actually rely on a mini purposeful system that somebody, a human operator, sets from the outside. So for example, you would set the temperature of your house thermostat for the temperature you want the house to be, and then the thermostat just keeps the house at the temperature you want it to be. But the interesting thing about these machines is that what we call the reference value, the goal for these machines, is always set by a human operator on the outside. Now, these advances weren't lost on scientists, and during the 40s, a group of scientists, and the most eminent being Norbert Wiener, pushed forward a field called cybernetics, where they took some of this understanding about controlling machines and applied it back to trying to understand psychology, which is an interesting full circle because the idea of negative feedback itself came from biological systems such as the homeostatic systems in the body for maintaining body temperature. But this was an opportunity to bring that understanding to try and understand the brain as a whole and behaviour as a whole. And very interestingly again, Alan Turing met with Norbert Wiener just a few years before he died. So there clearly was connections between these two men. Now, the thing about cybernetics is the field continues in some areas, but the term cyber has now come to mean computers or robotic or even the internet. The term cyber originally comes from the ancient Greek to mean steersman or oarsman. Its origins are all about controlling in a desired direction. But we're in this position now with digital and cognitive science where we think of the cyber movement or cyber anything as robotic, and we've lost the true meaning of the word. One of the reasons why this may have happened, now this is quite a detailed diagram, but it draws attention to the model of negative feedback that is still used in control engineering and for good reason in artificial systems. This is because artificial systems have their goals, as I said, set from the outside, and on the left of this diagram you can see the word input. So a control engineer uses the word input to mean the setting that the user makes to this device, which sets the goal that it needs to reach. Okay. Now, the interesting thing, if you think about living things, animals and humans, is that our goals aren't set from the outside. Our goals are set from the inside. We have our intentions, our motivations that are derived internally in our own nervous system. And Bill Powers calls this the input blunder, the assumption that living things should have the same structure of this negative feedback system as artificial, as machines. And also the assumption that a robot would have its goals set from the outside. Given that it's trying to emulate something living, surely it should have its goals set on the inside. And so by keeping this input on the outside of the system, the cybernetics movement still maintains this input-output linear model, despite the feedback that goes on. Another element that's missing in this diagram, which Bill Powers points out, is what's called disturbances. So the subtle things that go on in our environment that means that we don't necessarily get what we want and we need to act against them. In this diagram they're not shown, but they are critical in the model that I'm going to describe. So, given these issues with what I would say are issues with control engineering and cybernetics, how are we going to try and explain and model living activities that aren't the kind of logical activities that we know digital computers excel at? How are we going to design robots of the future? Now, I'm going to put it to you that there are certain tasks, everyday things that we do that currently the robots we've designed cannot do. So one of my examples I have every morning, I need to get dressed for work, get ready for work. At the same time, my two sons, one's 1 and one's 5, they want their breakfast. They each want their porridge in the cup and the bowl that they like, at the temperature they like, the consistency they like, which is different from each other. And somehow I've got to mix the porridge right, cook it, give it to them on a tray, mop up spills, deal with their little arguments with each other, and manage this whole process in the morning and still get to work on time myself. Now, to me, that is the kind of complex balancing of everyday goals that we all take for granted, but that clearly is beyond the reach of current robots. But it's interesting, there are robots that attempt to make things like porridge, even to make more complicated recipes. And this is a robot chef that exists, that has been trained to make a specific recipe. And it's trained by showing the computer thousands upon thousands of videos of chefs making this same recipe. And the robot tries to move its own arms and its own fingers and articulate them in the same way as a human chef in order to make the same recipe. And this is a classic way that robots are trained currently. But it's based on the assumption that the behaviours are what should be being learned and controlled and predicted. But the thing about this system is, if you were to move some of the objects around, it tries to do exactly the same behaviours as it did before and makes a massive mess of the whole process. Now, robots do include negative feedback in some of their designs, but I'm going to put it to you that negative feedback needs to not just be an afterthought to finely tune a robot, as is often used, but it needs to be the key component of the entire system, of the entire architecture, so that we don't have these very clunky robots in the future, and the ones that literally target their own perceptions, target what they need to perceive to achieve a task. Now, this is where I start to introduce to you perceptual control theory. I want you to look at the video in front of you. The person on the right is experimenter, the person on the left is a volunteer. And the person on the left has been given an instruction. They've been told what to do. What I'd like you to do is have a think, what is that person on the left with the green pen, what have they been told to do? Okay. Now, we've done research on this, and with about 300 people, and about 95% of them get the answer wrong. Let's see what you guessed, and let's see what the answer is. A lot of people say it's to draw a picture, and this looks even like a kangaroo boxing. Some people say it's to do the opposite of the person on the right, or to do the mirror image, or to act against them in some way. And all of those suggestions are actually wrong, and they're all based on the assumption that people plan and control their actions, because you see people's actions and you assume that's what people intended. But actually, what this person is doing on the left is controlling the position of the knot over the dot on this video. They're trying to keep the knot as close to the dot as possible. You can see that it's very close there, and the person on the left is having to act out against the person on the right and ending up drawing something, but only because they're trying to keep the knot over the dot. So what this shows us is that what people are doing is control, and what they're controlling is their perception, and in this example, keeping their perception of the knot as close as possible to the dot. Their actions are their means of control, the way they achieve that control of what they're noticing, what they're detecting. They're not actually planned ahead of time in detail, but behaviours emerge in the moment to achieve control. Here's an example from Konrad Lorenz, and here he is. These ducklings have come out of their eggs, and they're following him, keeping a constant distance from him. When he speeds up, they speed up. When he slows down, they slow down. And what they're doing with their legs in order to achieve this changes from moment to moment. But what they're controlling is their proximity to Lorenz. When we stand up on one leg, we have what we're controlling, which is for example, maybe our centre of balance. But if you were to do this and you just notice your muscles, they are changing all the time. You can feel them twitching from one side to the other. And what I'm going to put to you is that is happening on the fly all the time. What you're actually controlling is something more perceptual, something that you sense in your body. even when you do something like stretch your leg, that sounds like a behaviour. That sounds like a behaviour to be controlled. But how do you know when you stretch your leg just the right amount? Because you start to feel the pain, and you stop when it starts to feel painful. So you're actually controlling that perception of pain when you stretch your legs. We did a study where we asked people to copy a range of different images of different complexities. And we compared conditions where people were almost at ceiling, where they were copying it either directly or from memory. And we compared that to two sets of instructions where people hadn't seen the image. Either where we tell people what to do, how to move the pen, or we tell people what they should expect to see, what they should picture in front of them as they're drawing. And what you find, if you look at these two columns on the right, is that when you tell people how to move and how to behave, the accuracy of their drawings are far poorer than if you actually tell them what they should be perceiving. So sometimes I think when we think we're telling people what to do and it works, we're actually telling people what to perceive from their perspective. And this all comes down to the explanation derived from perceptual control theory. This is Bill Powers, who developed the theory in the 1950s and 60s. He was a medical physicist from the States, but he decided to develop a theory that would apply to the behaviour of living things. Here's a simple way of explaining the building blocks of perceptual control theory. So instead of an input from the outside, we have a reference value, a reference point inside the organism. Above the dotted line here is the inside, the nervous system of an animal or a person. And that's setting the goal. That's comparing its goal to its current input. So the current distance of the knot from the dot is what's being perceived. That's being compared to the desired distance, which is 0. That's creating what we call an error, which is driving actions, which through their feedback in the environment, through something that they're acting upon in the environment. In this example that you saw earlier, it would be the pen and the page and the rubber band. That is changing something in the environment that they are perceiving as they are doing it. And this is all happening continuously and changing all the time. This is not a stepwise input-output process. And all while that is happening, there's disturbances, there's things that are getting in the way, like the other person pulling the rubber band in the other example. And according to perceptual control theory, this model doesn't just apply to knots over dots, it applies to everything that we do. That we have just right states for all the things that matter to us in life, whether that be the temperature we like our porridge, whether it be the distance we stand from someone when we're talking to them, the level of excitement that we want, the level of anxiety that we're comfortable with, our need to be have a certain level of self-esteem, etc., etc. So these different things that we're trying to control, we're doing them all the time in parallel, and our actions are feeding back on our perceptions continuously in this closed loop. Now, one example where this is being shown to be particularly persuasive has been in the process of catching a flying object. And Rick Markin from Los Angeles has done a number of studies on this. And the ideal study to do from a PCT point of view is one where you actually build a model of the behaviour you're trying to explain. So rather than doing the sort of standard manipulation studies that we see of groups of participants in behavioural sciences, this approach tells us that really the way that we really can genuinely know that we've got an accurate model is to try and reproduce it using a simulation. So this is a simulation that Rick Markham produced, and it shows how a computer can get into the right location on a virtual baseball pitch to be in a position to catch a ball that's being thrown up in the air at a random location. And it works not by predicting the pathway of the ball, which is the standard view, not by understanding the physics or knowing logically where it's going to land. It actually works by just controlling two inputs, two perceptual variables, we can call them. And it does this because it has a virtual eye. And the virtual eye has a trace of the image on its retina. And what this little computer code does is it keeps the ball central in terms of its left to right location on the retina, and it also keeps the speed of the image on the retina, not the actual speed of the ball in the air, but the speed of the image on the retina at a constant value. And interestingly, if it does this, it ends up in the right position to catch the ball. So what this is showing us is that perceptual control can lead to a particularly efficient and accurate way of achieving an everyday act. Now, what this doesn't do is model the movements of the body and the legs. It's breaking it down into its components. And what I'll do is explain to you how you would do that using this approach. But it's still the same principle across the board, that all we control is the input at whatever level we're trying to explain a particular skill. This is a model that Max Parker, my PhD student, is working on with you, Lee, our software designer. And he's got a force feedback steering wheel, which we're using to allow a computer to use perceptual control theory to be purposeful, to control its inputs, and in this example, track a cursor laterally across a computer screen. And what we're doing, first we've shown here that you can, using this PCT model that has these internal reference values, that we can emulate the kind of tracking that you do as a person. What we're going to do from this is adjust it in a way to see if it can actually emulate different people's performance in terms of how they steer, because arguably different people have slightly different goals and they control for them in slightly stronger ways with different delays and that kind of thing. So we're looking to see whether we can both model the steering and also model how an individual steers using this approach. But if we really want to look at some of the most significant work that's going on in robotics based on perceptual control theory, then it falls to Rupert Young, and he's developed a large number of robots now that show proof of principle of various components of perceptual control theory. This one has the purpose of keeping that signal within the centre of its vision. And as you can see, what it's doing is it's moving both its head and its wheels in order to keep that centric. So again, that's the perception that it's controlling. And all those movements that it's doing to achieve that are being worked out on the fly. In the next video, what Rupert does is he uses perceptual control theory in an existing robot called a Baxter at Bristol Labs, and he uses it to emulate a Tai Chi movement. But the reason why we know this is a purposeful system working rather than a sort of planning behaviour system is that when you disturb it, and what Rupert's going to do is put a weight on its arm, it immediately adjusts for that and continues to mimic the exact Tai Chi movement regardless of the fact that it's got this weight on its arms. It doesn't have to learn or plan its actions differently. So I'm going to just skip to the bit in this video.
It counteracts unknown disturbances and engages gracefully with the loss of partial function. It also demonstrates the use of memory as the recall of perceptions as goals from which patterns of observed behaviour emerges.
So now watch Rupert as he puts the weight on. As you can see at the moment there's symmetry between the two sides, the two arms, because they're both using the PCT architecture. Now puts the weight on, a little bit of a perturbation, and it just carries on. Now, to do this, it's having to send out completely different forces, completely different motor commands to manage to achieve this exact Tai Chi movement. But it's not having to plan those in advance, it's just controlling for them automatically because of its purposeful nature, because it's working through this PCT, this perceptual control loop. And here is another example of a robot that Adam Matic produced as his master's thesis. You can look at this separately online, but I'm going to forward you in a moment to a section where Adam shows the robotic arm controlling pressure. So it's actually keeping a constant pressure of its little sensors onto a flat plate. And in order to do that, it's having to change and adjust its motors all the time. It's just here. So you can see this, it almost looks like it's stuck to the plate. It isn't at all. It only looks like it's stuck to the plate because it's constantly adjusting it to keep its sensors tight against that plate. Because that is its purpose, that's what it's aiming to control. Okay, this rather elaborate diagram would make nice wallpaper maybe, but it actually shows us that in the future we have the capacity, I think, to try and model much more complex things using this theory, because it has a very precise architecture for how these little units connect to each other, because the outputs of a high level system set the reference points, the goals for the level below, and the outputs of that set the levels for the system below, etc., etc. So there's a very exact way that we can do this, and Bill Powers described 11 different levels in this architecture. Now there may be more, there may be less, and he was open to be questioned about this. But Fred Nichols here has put together the levels that Bill Powers did specify, and he did this through his own introspection by thinking about what things he would control from a very basic level, and how he would need to build up new perceptions at higher levels to be able to control those at lower levels. So for example, we use our perception of intensities forms our the change in intensities forms our perception of a sensation as changes in intensity. That the pattern of sensations, either temporal or in a visual sense, for example, form a certain configuration that we can control. And configurations, their change over time, it's called a transition that we can be controlling as well, etc., etc. So the idea is that we achieve the very sophisticated activities and skills through ordering these control units in a hierarchy. And Bill Powers already had some very strong indications for what different levels of this system might look like. The fascinating thing also about these levels is that they were separately discovered by Franz Ploy, who is a primatologist working with Jane Goodall. And he found that during infant development in chimpanzees, they seem to be controlling for different perceptions at different stages of development. That they were marked by a sort of regression or disruption as they then overcame those and moved on to the next stage. And so what this tells us, partly because then with his work with his wife, Patty Dorit, they then found these same stages going on in human infants, and that's become what a popular selling book called The Wonder Weeks, and it explains why during infancy children have periods of disruption and clinginess that comes just before advances that they make in their skills and their abilities. And Franz Ploy has got some very impressive videos where he explains how PCT, which he discovered after collecting his data, really does explain the observations that he's seen in infants. But when we're thinking about robotics here, what this is also telling us is that we shouldn't expect this process of learning complex tasks to be easy, and we're probably going to need to emulate child development if we want to train a robot to be doing complex actions. And so we need to learn more about that way that this control hierarchy develops over time. And Bill Powers, in his books, explains in some detail the mechanisms for this. So I think in the future we will be moving away from an era of robots as kind of fearful or mechanistic, or obviously mechanistic agents, to a very different era. And here on this slide I want to bring together some key points to look to the future. Firstly, I want to point to the fact that people have commented that Alan Turing's work on morphogenesis could be used to help grow what's called soft robots that have certain patterns and shapes. Now, soft robotics is a real advancing area in robotic development, and in Bristol Labs it's one of their key directions, because this understanding that living systems have these soft components, so we need to emulate both the hardware and the software. But I think that's so interesting that Alan Turing's work is coming back in that way. Similarly, well, coming from what I've been talking to you about in terms of Bill Powers' work, here's a quote from Bill Powers. He says, "There is a backlog of unassimilated evidence all the way down to cell biology that negative feedback control is a basic principle of life processes." So here he is pointing to the fact that this negative feedback system isn't just unique to psychology. It's most likely going on in all kinds of biological systems that we've not given it credit for to date. And one example that Rick Markham pointed to recently is the fact that during cell mitosis, the centrosomes need to keep in a fairly exact position within the cell in order to do so, despite the fact that the cell is of such a changing fluid shape. And it would be very effective if negative feedback was what was responsible for keeping the centrosome in its right location. And that work hasn't been done yet, but there are all kinds of elements of the biology of living things that we maybe have looked at in this sort of cause and effect chain reaction kind of way, without realizing that actually it's much more sophisticated, and actually it's much more purposeful, and that these systems are constantly sensing levels of variables and adjusting them dynamically. And finally, I want to bring back what I was mentioning in terms of analogue computing. Here's a quote from Professor Stephen Ferber at the University of Manchester, where he says, "All of the processing in neurons and synapses uses much more efficient analogue chemical techniques." So what he's saying there is, if we want to emulate how the brain processes information, we would really should be using analogue rather than digital computers. And there is work now building analogue machines. So what I see as a humble psychologist, but one who's encountered perceptual control theory and read Turing and looking at this emerging field, is one that combines these components: soft robotics, negative feedback control, and an analogue process, and this hierarchy that Bill Powers has so eloquently described. So that's my kind of end point, really, in terms of starting off at Alan Turing's rather spiritual beliefs against his very amazingly technical brain, how that's echoed in how science has progressed, but how we need to revisit and question some of those assumptions, some of which Turing made to great effect in terms of the digital revolution, but to almost start from scratch again and build up computers and robots in a very different way, in a way that emulates life, and a way that actually sees purpose and intention as part of science rather than something very different. And I think, therefore, in the future, we might be having these kind of robots. This is the Baymax from the film Big Hero, and the ones that we don't need to be afraid of, but actually provide us with the kind of things that humans need as well. And so I've kind of want to leave you with this image as I draw close to the talk. Thank you.